Welcome to this video. If you want to truly understand monoclinic materials, how they are defined, and how their stiffness matrix is formulated, stay with me. In this video, we will build the concept step by step, starting from the general form of Hooke's law and material symmetry, and then use these ideas to derive the stiffness matrix of a monoclinic material. Let's start with the most general form of Hooke's law. When we consider the symmetry of the stress and strain tensors, we can rewrite each tensor as an array with 6 components. To relate these two 6-component arrays, we need a 6x6 stiffness matrix. At first, this matrix contains 36 independent components. However, the story does not end there. The elastic energy of a material is a function of strain, and its second derivatives with respect to strain are symmetric. As a result, the stiffness matrix must also be symmetric. In other words, the components shown in blue and red are equal. Therefore, instead of 36 independent constants, we only need 21. Now, before introducing monoclinic materials, we need to understand one important concept: material symmetry. Imagine a material whose internal composition is symmetric with respect to a plane. If you look at the material from one side of this plane, its composition is the mirror image of what you see from the other side. And because the material is uniform in this direction, the same symmetry applies to all planes parallel to this plane. An important point here is that we are talking about the material itself, not its external geometry. The shape of the specimen does not determine material symmetry. What matters is the symmetry of its internal composition and properties. Now we can introduce monoclinic materials. A monoclinic material is a type of anisotropic material that has one plane of material symmetry. As a simple example, consider this combination of two different materials. The resulting material is symmetric with respect to planes whose normal direction is parallel to the first material axis. So, how does this symmetry affect the general stiffness matrix? How can we simplify the 36-component matrix for a monoclinic material? To answer this question, we need to look at the loads and responses with respect to the plane of symmetry. In this example, the plane of symmetry is the 2-3 plane. The stresses and strains can be divided into two groups: symmetric and antisymmetric, with respect to this plane. The symmetric components include the normal stresses and strains in all three directions, together with the shear stress and strain that lies within the plane of symmetry. The remaining shear components are antisymmetric with respect to the plane of symmetry. These correspond to shear in planes perpendicular to the symmetry plane. And here is the key idea. If the material is symmetric with respect to a particular plane, applying a symmetric load produces a symmetric response. Likewise, an antisymmetric load produces an antisymmetric response. Therefore, symmetric and antisymmetric components cannot be coupled through the stiffness matrix. This allows us to identify the zero components directly. For example, these 6 components would couple the normal stresses, which are symmetric, with the antisymmetric shear strains. Because such coupling is not possible, these components must be zero. Similarly, these two components would couple the symmetric shear stress with the antisymmetric shear strains. They must also be zero. Therefore, 8 components of the stiffness matrix are zero. Now we can write the stiffness matrix for a monoclinic material. And remember, the stiffness matrix is symmetric. So, the components corresponding to those 8 zeros on the opposite side of the matrix must also be zero. As a result, the final stiffness matrix contains only 13 independent material constants. So, starting from 21 independent constants for a general anisotropic material, the presence of one plane of symmetry reduces the number to just 13. And this is the fundamental stiffness formulation of a monoclinic material. Finally, let's look at a few real-world examples to better understand monoclinic materials. A simple and familiar natural example is wood. If you look at the cross-section of a tree trunk, you can see the growth rings. These rings remain approximately constant along the length of the trunk. As a result, The planes perpendicular to the axis of the tree trunk can be considered planes of material symmetry. Another important example is unidirectional composite materials. In a unidirectional composite, the fibers are aligned in one direction. The plane perpendicular to the fiber direction can be considered a plane of material symmetry. These examples help us connect the mathematical formulation of monoclinic materials to real materials that we encounter in engineering and in nature. I hope this video helped you understand the concept of material symmetry and the stiffness formulation of monoclinic materials more clearly. If you found this video useful, please like the video and subscribe to the channel. It really helps us create more useful engineering and simulation content. And if you are interested in Abaqus, finite element modeling, and engineering tools, make sure to visit our website. You can find a range of useful Abaqus plugins, tools, and engineering resources there. Thank you for watching, and I'll see you in the next video.